Hello everyone, am I audible? Okay, you both gave the contest yesterday, Codeforces.
Yes, yes, they do.
Okay, how many problems are you able to solve?
Three problems. I solved the two problems.
Okay, let's start the post contest discussion. Is my screen visible? Okay, the first question is race. Like two people are there, they're participating in a game show. And the prize will be dropped at a certain point. They gave 2 points, X and Y. They don't know, like, it might fall at 2 points, at X or at Y. And Li's point is chosen at A. Bob wants to choose point B, that is other than A. So he reaches the point X or Y easily at the shortest time rather than A. And the distance between 2 points is modulus of C minus D. Any approach? Hello.
Yes, Dili, I will uh, do one thing. I will iterate to one to maximum value of A or B or A, X or Y, and I will check if that I will be like compare the given condition. If it true, we will break it and we can yes. Other, otherwise, no.
Okay, let's discuss it. The test case is 134531. See, the first is LIC is at A, LS A is at 1 and X is at 3 and Y is at 4. Bob has to choose at a point so that he can reach X or Y easily than A. So here the answer will be 2 or 3 or 4. So the distance between 1, 3, 4. If Bob chooses 2, then the distance between 2 and 3 is 1 and 2 and 4 is 2. And it is less than 1 and 3 the distance is 2 and 1 and 4 the distance is 3. So in the both the cases Bob is at the position, so it is he can reach the position X and Y faster. Am I audible? Are you understanding? So I thought of one approach. Bob will be choosing 2 points B and C. The value of B will be A plus 1 and the value of C will be A minus 1, because they told A is not equals to B. So we will be choosing point after this is A. Let's suppose X and Y. We'll be choosing point B here and we'll be choosing point C here. If the values of X and Y are in the left hand side of the number line. So if the point B or C, it is it reaches the point X or Y less in less time than compared to A, that will be our answer. If one case is failed, then the answer will not be coming. So that A can reach. easily X or Y. So let's go to the coding part. We will be calculating the distance a minus x, this distance 1, and distance 2 is absolute or absolute difference between a minus 5. Then we will be taking 2 points, b is equals to a plus 1, c is equals to a minus 1. We will be comparing absolute of x minus b, that point distance is less than the ls distance, and y minus b is less than the ls distance. If both conditions are passed, then we will be giving s. Otherwise, we will be checking the c point. If both conditions are passed, then we will be giving s. Otherwise, no. Did you understand?
Yes, Didi.
Okay. Any doubts? Or should I explain with another example? Okay, let's go to the second question. The second question, they said the array is beautiful if the distance between the two adjacent elements is less than or equals to 1. Absolute difference between them is less than or equals to 1. Otherwise, we have to try to make it beautiful. If it is not possible, we have to output minus 1. We have to choose an index such that minimum and maximum value of those, and then in between them we have to replace it. Let's take one example. One, see the value, the difference between absolute difference between 3 and 3 is 0. So which is less than or equals to 1. So it is possible. Number of operations required is 0. Because it is also already a beautiful array. In this example, 3137. The adjacent difference 3 minus 1, absolute difference is 2, and 1 minus 3 is also 2. Then after 3 minus 7, it is 4. So this is not a beautiful array. In this case, we have to choose two elements such that we have to replace those two elements by the value c, like 3 1 minimum is 1, and 1 3 1 maximum is 3. We have to replace by 1 or 2 or 3, such that we can make it a beautiful array. If we replace it by 3 or 2, 2, 3, 7, or 3, 3, 7, the absolute difference between these two is less than or equals to 1. So we need one operations. In this case also, we will be the difference between 1 3 is 2, 3 5 is 2, 5 2 is 3. We will be replacing 3 and 5 with minimum is 3, maximum is 5. We can replace any element between 3 and 5 inclusively. So we will replace this by 3. 1, 3, 2. Now the absolute difference between these two is 1. So we got the beautiful array. And if the elements are two elements, 6 and 9, we cannot replace it with, if we replace it with one element, we need at least two elements. So we cannot do it. So the answer will be minus 1. Did you guys understand?
Didi, can you explain the beautiful array part?
The absolute difference between 1 and 3 is 2. Absolute difference between 3 and 3 is 0. Absolute difference between 3 and 7 is 4. So the difference 0 is less than or equals to 1. It is given in the question that a B is beautiful, the array is beautiful if the difference between the adjacent elements is less than or equals to 1. It is already a beautiful array. So the number of operations required is 0. Did you understand?
Yes, Didi.
When we take 3, 1, 3, 7, there are no two elements such that their absolute difference is less than or equals to 1. So we have to choose two elements. Suppose I choose 3 and 1. I should replace it with minimum of, see here it is given in the question. Choose an integer x such that minimum of a of I comma a of I plus 1 is less than or equals to x is less than or equals to max of a of I comma a of I plus 1. Minimum of 3 comma 1 is less than or equals to x is less than or equals to max of 3 comma 1. So 1 is less than or equals to x is less than or equals to 3. So the possible values of x are 1, 2 and 3. So if we replace 3 and 1 by 2 or 3, like 2, 3, 7 or 3, 3, 7, then the absolute difference between the adjacent elements is less than or equals to 1. This is 1 and this is 0. So we are converting this array into this array. So the number of operations required is 1. Are you clear now? Hello? Anyone has any approach? Hello? Am I audible?
Yes, you're audible.
Am I audible?
Well, guys, wait a minute. She was having some issue joining first.
Am I audible? Is my screen visible? Okay, do you guys have any approach for the second question? Hello?
Yes, Didi. Uh, First, um, the first impression of the question is that if adjacent elements are
Okay, let's go to the approach.
adjacent.
Okay, tell your approach, Shubham. Okay, first we will be traversing the array. We will be checking if there is an if there is such pair such that the difference between them is less than or equals to 1. We will be returning and the number of operations will be 0. And if there are only two elements and the absolute difference is not less than or equals to 1, then we will be printing out -1. Are you understanding? Hello, am I audible? If the array is 2, 4, 6, 8, is it possible to make a beautiful array? Hello.
No, they don't.
Yeah, we cannot make a beautiful array because if we replace 2, 4 by 3 or 4, 4, 6, 8, again the difference will be 2. Again, if we replace 4, 6 with 6 and 8, again the difference is 2. It's not less than or equals to 1. So we cannot make. In that case, either if it is a increasing or decreasing, like sorted, then we cannot make it a beautiful array. So we have to choose such that in array there should be an element that is reverse of it. If it is increasing, at one point it should be decreasing. Like one element, 2, 4, 8, 6. Now can we do it? Beautiful array. Yes, we can replace 4 and 8 with 6 because 4 and 8 minimum element is 4 and the maximum element is. So we have to choose x in between 4 and 8 inclusively. So if we choose 6, 2, 6, 6 or 2, 7, 6. So the minimum difference between 6 and 6 or 7 and 6 is less than or equals to 1. So we can make a array beautiful if it is totally increasing and at one point it is decreasing, or totally increasing at one point it is decreasing. So we'll be writing if a of, at first, like, we'll be checking according to the first element, first difference. If a of 1 minus a of 0 is greater than 0 and a of I minus a of I plus 1 is greater than 0, that means the total array is in increasing order. So this at this point we'll be continuing. In the same case, if it is decreasing also, we'll be doing the same thing. If these conditions are not satisfied, then we will be making a variable x is equals to 0, which is initially x is equals to 1, and then break it. So we found a point such that where The element is not totally increasing or not totally decreasing. So then we'll be printing out cout one operation is required. Otherwise, if it is reached at the end position, then we will be printing -1. Did you understand? Is there any doubt? Should I explain it again? Hello, am I audible?
Yes, DB.
Okay, we'll be going to the coding part. Is my screen visible? Okay, the main function for all the test cases we'll be solving it. We'll be taking the size of the array and we'll be taking input of the array elements. The first we'll be checking is if there is at least one pair such that the difference less than or equals to 1, then we will be giving 0 and then return. We'll be checking if n is equals to 2. This condition is already checked. And if n is equals to 2, then -1. For the remaining cases, like if like C out 1 will be there. We'll be traversing the whole array. If it is either increasing or decreasing, we'll be continuing. If else we found any other point, like it is not totally increasing or totally decreasing, then we'll be breaking it. We'll make x is equals to 0. If x is not equals to 0, then -1. That means it is totally increasing or totally decreasing, and the absolute difference is not less than -1. Otherwise, 1. Did you guys understand?
Didi, I have a doubt.
Okay,
Hello.
you can ask.
Uh,
You can ask the doubt.
what if the operation is greater than one?
No, it is not possible. See, like 2, 4, 8, 6. The difference, like we will be replacing 4 and 8. Like at one point it is decreasing. Up to here it is increasing and decreasing. So, uh, in between these two, this element definitely exists.
Okay, can you take one example?
2486 or any other.
Any other one?
Okay, you say me example if you don't mind.
1, 2,
1, 2,
8, 6,
8, 6,
uh, and 2.
2. Already
Yes.
the absolute difference between 1 and 2 is
Okay,
1.
okay.
It is less than or equals to 1.
Yes, yes.
Can you make it 4?
Wait, 1 second.
Hello.
1 second, please.
Okay. Okay.
Yeah. Yes. One example is 1,
1,
12,
12,
10,
10,
7,
7,
2.
2.
Yes.
See, here 1 and 12. In between 1 and 12, the minimum is 1 and maximum is 12. We can replace it with any elements between 1 to 12.
Yes.
So I will replace it with 10 or 11.
Okay, they understood.
Okay. So the absolute difference will be less than or equals to 1. Any doubts?
Not
Okay, the remaining questions will be taken by the Sandeepa.
Hello, am I audible? So we are approaching for the C problem. Is the screen visible? Okay. So in the C problem, Alice and Bob are given an array A, and where initially all the elements are colorless, and Alice chooses any three elements and color them red, and Bob will choose any of the element and color it blue. It may be one of the red elements also, and the winning condition is for Alice. Sum of all the red elements will be strictly greater than the value of that blue element Bob choose. Okay, and we have to find all the possibilities how Alice can win the game, and in regardless of Bob's any action. Okay, and we have the array given here, and we have to print the three elements in order to win the regardless of the Bob's action. Okay, so here we can see this example. We will explain. So in this example, you can see uh, if Alice chooses 1, 2, 2, then Alice's total sum will be 5. Okay, and to eliminate this, Bob may choose the maximum element 4, but still there 5 will be greater than 4. Or otherwise, if Bob chooses 2, these two, then red element's total sum will be 3 and Bob's will be 2. So 3 greater than 2, Alice wins. So in this case, we have two possibilities. One, the first one, and these two, and second is the second one and these two. So there are two winning chances. Okay, so my code is that basically we will take a max 1 and max 2. Max 1 will be the most maximum element. First we will sort the array whatever the array is given, and max 1 will be the maximum element and max 2 will be the second max element. Okay, and the first case, let me show the code. Yeah, from this, uh, we have first sorting the array, and here we can see race equal to 0, so race will store the final total number of possibilities, and we will start from index traversal from I equal to 2 to n. That I index will be the third index or the maximum value that Alice will choose, and the other two values will be lesser than that, means it will be in the left of that. So for worst case it will I must be equal to 2, because the 0, 1, 2 may be the lowest possibility. So I traversing starting from 2. And first of all, we are having two variables, one double val and one ref val. These are the values for Bob's turn. Worst case scenario, Bob's turn will be that. Why in the double val I am taking 2 into AFI? Because suppose this case. Yeah, when 1 to 2 is taken, then if Bob chooses these two, then the sum will be 1 plus 2 plus, if I taking the total sum, then that will be 1 plus 2 plus 2, and for the Bob's part it will be normal 2, and as I have added, wait a bit, then let me write, red will be 1 plus 2 and blue will be 2. So if we add here, you can see, so if we add both side 2, wait, 2, both side 2, still it's 5 and 4. Okay, so both side we are adding 2, it's 5 and 4. So here you can see when Bob chooses the maximum element whatever red has chosen, then the Bob's turns total value is becoming twice of that. This is one case, and the other case will be when Alice chooses wait a minute, Alice chooses 1 2 2, and Bob chooses 4. So 4 is the maximum element of the array. So in this case, Bob takes 4. And this case we are defining by the ref val. And for this case, we are defining by the double val variable. That's the reason here you can see the codes. If Bob takes a of A, Alice left with 2 star A of I sum. Okay. And ref val will be the maximum possible value Bob can pick, worst for Alice, that will be okay. And when I, because we are traversing for a particular index, when that particular index here taken for the last value, then Bob has to choose the second maximum value. That, like, I am assuming the I in such a way that that ith index will be particularly red. Bob can't choose that particular to blue. Okay. And the target, we are assuming target, whatever target is the sum of the remaining two elements of the red elements, whatever Alice must make from the left side of I. Okay, here you can see for this case. Yeah, so for I equal to 2, like where here, so in the left we have 1 and 1. Okay, and double val will be 2, 2 into 2, and ref val will be 4, the maximum, so target is 2. Okay, and here we have to check the possibilities. And for, so here you can check that target is 2, so Alice minimum have to make here 2. So 2 plus 2 can be 4. Minimum, yeah, so 2 plus 2 can be 4, and it can beat the Bob's move. Okay, and here we left equal to 0 and right equal to I minus 1. So we are traversing in the left side of the index I we have assumed. So this portion whole code is calculating the all cases where the pairs will be taken by Alice in the red, so that we can beat the target value. Like we have given the condition of the code. Uh, wait a bit. Alice wins when if the sum of the red elements is strictly greater than, you can see. So strictly greater than, the sum must be here greater than the target value, not greater or equal to. Okay. So when that is the greater than, so we are adding the cases result plus equal to right minus left. This will particularly take all the cases when the left and right pair will be, right will be I minus 1 and left will be 0. Okay. And if this pass, then we will do right minus minus to check if also the lower value of that, here, like here when I is here, so there it can't move because low and high will be equals. So here you can see if we take in the left of that, right here low will be first, you can see that case low will be 0 and right equal to 1. Okay, so their sum is 2 and we have target 2, so 2 it becomes equal to 2, not strictly greater than 2. So there is no possible case, so we are defining race equal to 0. And according to the code here, right becomes left, moves 1 point left. So if right becomes 1 point left, then left and right will be 0. So the condition fails and it gets out of the loop. Okay, so that's how we will continue the whole code, and we can see that the total number of cases of the left and right pointer will count whatever Alice will choose red points in the left of ith index. For I equal to 3, we can see the dry run. I equal to 3. Double val will be 4 because that element is 2, and ref val will be 2. Ref val, wait a bit. No, ref val will be 4. Sorry, ref val will be 4, and target will be, because 8 is maximum, so target will be 8 minus 4 and equal to 2. Sorry, this one I am talking. Yeah, so target will be 2, and in this case you can see left pointer is 0 and right pointer is 2. So this, their sum is 3, which is greater than 2. So defining race equal to r minus l, so adding 2. So in this case you can see the two cases will be 0 2 3 and 1 2 3 indexes. Whatever are total possible chances, 0 2 3 and 1 2 3. You can see this example. And after traversing this case, if I do l, right, l equal to 0 and wait a bit, l equal to 0 and r equal to 1, then you can again see our sum according to previous value is 2 and our target is 2. So 2 is equal to 2, not greater. So nothing check. So nothing there will be checked and the loop will break again, while loop, and we will go to for I equal to 3 case. Okay, sorry, I equal to 4 case index. For this case you can see the double value will be 8 and the reference value will be 2, because fourth in this case, so the second best is will be this one. Okay, and target will be 4. So target is the most value of the left and right pointer sum. uh, Alice has to make red. Okay, so there we can check uh, l equal to 0 and r equal to 3, that is the sum becoming 0 and 3. So 0 and 3, so 3 is less than 4, so there is no possible cases we can see. And further, if we do r minus minus in the according to the code in the left we are checking, then there are no other possible cases. So finally we can conclude, and I will break the for loop. The raise value will be 2. So this was my whole code for this program. Have you understood? Okay. So I am moving for the DIV code. Okay. Wait a bit. Yeah. So this is the fourth one and the last question today we are discussing. So we are given a basically tree, and even here two distinct vertices in the directed graph, and ordered where UV will be good if there exists a path from vertex U to V along the edges of the graph. Okay, so a good pair will be a basically a directed edge or directed path. Like here you can see 3 to 2. 3 and 2 is a directed path. That was a good pair. 3 or 1 and 1 and 2 are also good pair. So basically n vertices and n minus 1 edges given of a tree, and we have to determine whether it is possible to assign a direction to each edge of the graph, so that number of good pair will be n. N is the number of total vertices. Okay, and if this possible we have to print the edges, directed edges. Fine. So basically I am telling my approach here. First of all, see, uh, we will assume a center value of the element. First of all, we will make an adjacent matrix. See the code here. Yeah, so this will I will make an adjacent matrix here. You can see adjacency list, sorry, where we will store each and every undirected edges by u and v, and we'll store their edge IDs also, because we have to keep track of the edges what are visited. Okay, so we'll store their edge ID and the indexes, yeah, nodes. Okay, this will be an adjacency list. So for this example we are dealing, this will example there are 1 and 2 2 4 1 3 3 5 are edges. So the adjacency list you can see, 1 has adjacency list of 2 comma 0. 0 is the zeroth one edge. Okay, and 1 also connected to 3, so there you can see 3 comma 2. 2 because it is appearing in the second index of the edges list. For 2 you can see overall the adjacent 2 is connected to 1 and 4, 3 connected to 1 and 5, and 4 connected to only 2, and 5 connected to 3. Okay, So basically, first of all, we have to find a center value. What is a center? Center is the first index, like vertex, where we'll have two values. Like when we are appearing, traversing over the adjacency list, the size of the adjacency list will be minimally at least two, so that we are connected to two separate nodes. Here you can see the first for one index is connected to 2 and 3 according to this diagram. This is the final tree. We'll see later. So first of all, you have to find a center value. Okay, for traversing the adjacency list, whatever the first value will face of size 2 will be assigned to center. The center is essential because we will assign the direction. Like this example, you can see 1 is assigned the center, so 2 and 3 are connected, so we will connect in such a way the directed edges so that this becomes a path, like 2 to 1 one edge and 1 to 3 another edge. So the main 2 to 3 we will get another edge. Okay, this is the main routing will main and basic plan of the first approach. Like how to approach this question, this is the most essential point. First of all, we have to put a center value. If we don't find a center value, then we'll return impossible. This is not possible to make such a tree with n good pairs. So this one will be 2 to 3 will be one of the good pairs. So first we are getting three good pairs from three vertices. Okay, if we do not find a center, returning no. Fine. Here you can see. So we will take a used vector for adding the those indexes and calculating, like this is like a visited array similar value. So we will take, so for the whatever edges have been already visited, to keep count of those. Okay, and traversing from starting from the center one, we have whatever connected to center. You can see two connected and three connected. So u1 and u2 are the two vertices connected to center, and we will point first of all. uh, Here you can see u1 to center is pointed and center to u2 is pointed, and result is the our the final array, whatever we have to return the directed edges. Okay, and this is the used edge is the correct count of those visited array similar like that. And result, we are pushing u1 comma center and center comma u2, because the directions we have explained, u1 to center and center to u2, so the ensures a path u1 to u2 via center. So we have three paths already through the center. This is the starting point. Okay, and we will keep count of one of the stack values, so and push those values. Like we are pushing stack u1 comma center comma 1 and u2 center 0. 1 is for the direction where it is pointing current to parent node, and 0 is for the direction when parent node to current node is pointing. Okay, so you can see center is the parent node and u1 and u2 are the current nodes. So here we are, as we are doing u1 to center, so we are pushing u1 center 1. Okay, so the now we will do a basic DFS operation. We will pop the topmost element of the stack. And first of all, tell how many of you have studied graph DFS traversal like things. Have you studied? So you will take understand easily. Hello, am I audible? Hello,
Hello.
am I audible?
Yes, yeah, you're audible.
You have studied graphs concept, BFS, DFS
Yes,
traversal.
I know graph.
Okay, okay. So you will keep track of that those things. This is similar to graph. This is also DFS traversal. Also, we will take a stack and put the particular those indexes. One where the 1 and 0 are maintaining for the directions. Okay, and this is the parent node, and this is the current node. So till we will continue till stack finds
Yeah,
empty.
one second. Line number 49. Can you explain?
49. This one.
Yeah,
This one.
this one.
Oh, I am. This is used is basically a visited array. Like you deal with the visited array, not to keep count of in DFS traverse or whatever nodes already been visited, so we don't visit them again. That is we are taking. So this is because ID1 and ID2 are the edge IDs. We are keeping track of the whatever has used. Like we are in this example, we are pointing already like 2 to 1 and 1 to 3 for initially pointing because 1 is the center value. Okay, so we are keeping track of the visited array so that particular edges are already been count. You understand those ID1 and ID2 are the particular starting edges.
Okay, man. Understood.
Like we are keeping track of the visited array kind of thing. Okay, so this is the main operation. We will pop one of the top value, and that particular top value will be, we will take the current node, parent node, and the direction, and we will traverse through its neighbors, and we will put its neighbor in the stack again, and this will operate like a DFS loop everywhere we see. So first of all, this is basic loop. We are adding the checking all the neighbors of the current node. Okay, so the neighbors will be first of all p dot first and p dot second, and eid for marking the used edges. Like you are asking Shubham, here you can see that if the used is already been used, so we continue, not check this case. Check for the next neighbor, or if not, then we will mark true and check for this. This is the main operation portion. Okay, so you can see the dry run here. Yeah, so E1 will be 2 and U2 will be 3. Okay, this is already pointed and pushed to the stack. Stack is pushed 211 and 310. So top will be 310. Here you can see. So for the current node, like this already pushed. This you can see 221 and 123. This is already pointed. So 310 current node is 3. Okay, so current node 3, and it's whatever is neighbor, it's neighbor 5, because you can see 3, one node already visited, so one will not check again. So this next neighbor is 5 and 3 is its edge ID. Okay, so parent node is 3 and neighbor is 5 and direction is 0, because direction this one is printing here. So for this we will check this formula. Okay, remember this because we will have to find at any node there will be two opposite directions. Like if 1 to 3 is connected, then it will be 5 to 3. Like here you can see if 2 to 1 pointed, then here we will point 2 to 4, not 4 to 2, because this way will ensure that there is exactly n good pairs, like n directed edges. This is the main concept here. So if parent to current is pointing, then we will point neighbor to current, because so that these points parent to current and current to neighbor all are incoming towards current. And if current to parent is pointing, then we will point current to neighbor, so that current to neighbor and current to parent is point, all are outcoming edges. Okay, so we will push 5 3 1, because we have pointed 5 to 3. This already been pointed in the directed edge. Okay, and added to the result. Here each step we are adding this to the result. Okay, and then we are pushing this neighbor. Then in the next step, neighbor will be the current value and current will act as the parent. And as the direction was initially 1, so it will now push 0. And for 0 case it will push 1. You can see here, as the direction was initially 0, we will put 1, because the reverse case, we can see 1 to 3 was put to this direction. So to reverse this, we will take that every time it will be a reverse edge. We will push this 0 direction, 5 to 3 5 3 1. Fine. Now the stack top will be 5 3 1, and as 5 has only third node, this is already been visited, so no neighbors to check. Okay, so both of the two elements will be popped from the stack, and the last element remaining will be 2 1 1. Now these two will be checked. Okay, these two will be the current node, and 2's neighbor are 4, because you can see 1 is already been visited and 4 is the current node. Okay, so for 4 we will assign, because we can see we have pointed previously 2 to 1. So this time we will point 2 to 4, as I have said, to opposite directions according to this formula. If current uh, hmm, if parent to current is pointed, then neighbor to current will be point to maintain this like structure. Okay. Hmm. So 2's neighbor is 4 and the direction is 1. So we will pointing 2 to 4 and pushing 4 to 0. So current node is 4 and its parent is 2, and according to as the direction initially was 1, it will be reversed and pushed to 0. Okay. Now the stack top will be 4 to 0. Nothing left in the stack. And as we can see, 4 has only one element, 2, and that 2 second node is already been visited. So finally the stack is empty and all edges been visited, and the final graph is similar like this. This is 2 pointing to 1. 1 is our center node, 1 the center. Yeah, 1 is center our, and you can see here to how many good pairs are there. 2 to 1 is a good pair, 2 to 1, 1 to 3, and 5 to 3. Yeah, and 2 to 4, and last one is 1 3 taken, 5 3 taken, 2 1 taken, 2 4 taken left. Oh ha, the last one will be 2 to 3. That's okay. So we are having 5 good pairs. You can see the code. This is the whole neighbor operation, because as I have explained, if current to parent is initially pointed, then we will point current to neighbor so that this structure is maintained. Okay, and after the stack is empty, whole stack is empty, we will have the our result, and we'll push the p dot first and p dot second, all the directed edges we will print. So this was my approach basically. Have you understood or any doubt?